When astronomers first pointed the most powerful telescope humanity has ever built toward the deepest, oldest light in the observable universe, they expected to find galaxies. Faint, young, still-forming galaxies, exactly the kind of thing this telescope was built to find. What they did not expect to find was hundreds of small, strangely uniform, deep red dots scattered across the earliest images of the cosmos, glowing with a color and a brightness that didn't match anything in the established models of how the early universe was supposed to look. Years later, scientists still don't have a complete, agreed-upon explanation for what these objects actually are. This is the story of one of the strangest open mysteries in modern astronomy, hiding in plain sight in some of the most famous images ever taken of the universe. The story begins in the summer of 2022, when the James Webb Space Telescope released its first deep field images. These images captured light from galaxies so distant and so faint that the light reaching Webb's mirrors had been traveling for over 13 billion years, meaning astronomers were looking at galaxies as they existed when the universe itself was only a few 100 million years old, a tiny fraction of its current age. This was exactly what Webb was designed to do. Its predecessor, the Hubble Space Telescope, had captured its own deep field images decades earlier, but Hubble's instruments were tuned primarily to visible light, and the light from the earliest galaxies has been stretched by the expansion of the universe into infrared wavelengths effectively invisible to Hubble's cameras. Webb was built specifically to see in that stretched infrared light, giving astronomers their first real, detailed look at the universe's earliest chapter. And almost immediately after the first deep field data started pouring in, astronomers noticed something strange. Scattered among the faint, fuzzy smudges of early galaxies were small, compact, remarkably red objects. Not just red in the sense of appearing reddish in a false color image, but red in a very specific, scientifically meaningful way. Their light was heavily weighted toward longer, redder wavelengths, and dropped off sharply at shorter, bluer wavelengths, producing a distinctive V-shaped signature in their spectrum that researchers hadn't seen described in any pre-Webb model of early galaxy formation. At first, a handful of unusual objects might simply be an oddity, a statistical fluke buried in a dataset otherwise full of ordinary galaxies. But as more and more deep field data accumulated over the following months and years, the numbers kept growing. Researchers, scanning through Webb's early observations, began identifying dozens, then hundreds of these objects, compact enough to appear almost point-like even in Webb's remarkably sharp imaging, and consistently red in that same characteristic way. Astronomers began referring to them, somewhat informally at first, simply as little red dots, a name that has stuck in the scientific literature ever since, appearing in the titles of published papers, despite sounding more like a description a curious child might offer than a formal astronomical classification. So what exactly are these things? This is where the story gets genuinely interesting, because the honest answer, even now, is that astronomers are still debating it, and the debate itself reveals a lot about how difficult it is to interpret light that has traveled across almost the entire history of the universe to reach us. The leading, though still contested, explanation is that many of these little red dots are actively feeding supermassive black holes, sitting at the centers of very young, very early galaxies, surrounded by thick, dense clouds of gas and dust. As material spirals into a black hole, it heats up dramatically and radiates enormous amounts of energy, a phenomenon astronomers call an active galactic nucleus. If that energetic core is embedded in enough surrounding dust, the dust can absorb and re-emit the light in a way that pushes its apparent color strongly toward red, while also concentrating the light into an extremely compact, point-like source rather than a broad, extended galaxy. Under this interpretation, the little red dots aren't just galaxies, they're galaxies with unusually active, unusually well-hidden supermassive black holes at their hearts, caught in a phase of vigorous early growth. If that explanation holds up, it raises an entirely new puzzle of its own, one connected to a much older mystery in astrophysics. How do supermassive black holes, some of them billions of times the mass of our sun, manage to grow so enormous so early in the universe's history? Standard models of black hole growth assume a relatively gradual process, matter slowly spiraling inward over long stretches of cosmic time, limited by a natural physical speed limit on how quickly a black hole can absorb material without the resulting radiation blowing the surrounding gas away before it can fall in. But if little red dots really do represent a widespread population of actively growing supermassive black holes existing when the universe was just a few 100 million years old, that population suggests black holes were reaching significant masses far earlier and possibly far faster than these standard growth models comfortably allow. In other words, these strange red smudges might be showing us black holes caught in the act of breaking the universe's own supposed speed limit for growth. But that's only one interpretation, and it's important to be honest about the fact that it isn't universally accepted. A competing explanation suggests that at least some of these little red dots might not be dominated by black hole activity at all, but might instead be intensely compact, extremely dense clusters of ordinary stars forming and burning in tight, chaotic bursts within very young, very small galaxies. Dense starbursts like this can also produce concentrated reddened light if enough dust is mixed in with the forming stars, absorbing and re-radiating starlight in a way that could, in principle, mimic some of the same observational signatures researchers initially attributed to hidden black holes. Untangling which explanation applies to which specific little red dot, or whether some of them might represent a combination of both processes happening simultaneously, has become one of the more active and genuinely contested debates in observational astrophysics since Webb's data began accumulating. Adding to the mystery, astronomers have also identified genuinely strange behavior in the spectra of some little red dots that doesn't fit neatly into either simple explanation. In several cases, researchers have detected extremely broad emission lines in their spectra, the spectral fingerprint typically associated with fast-moving gas swirling in the intense gravity extremely close to a black hole. This kind of signature is a strong, fairly direct indicator of black hole activity, lending real weight to the black hole interpretation for at least a significant fraction of the population. Yet, at the same time, other observations of these same objects have shown puzzling features that don't perfectly match the behavior of well-understood, actively accreting black holes observed in the more recent, much closer universe, leaving open the possibility that whatever is happening inside these little red dots represents a genuinely different physical regime than anything astronomers have directly observed before, perhaps some early transitional phase of galaxy and black hole growth that simply doesn't have a close analog in today's universe. There's another layer to this mystery that deserves real attention. Little red dots appear to be strangely, almost suspiciously common in the early universe, and then largely vanish from view as cosmic time moves forward. Surveys combing through Webb's deep field images have found that these objects show up in significant numbers when looking back to when the universe was very young, roughly its first billion years or so, but become dramatically rarer in observations of more recent cosmic epochs. If little red dots really do represent an early, active phase of supermassive black hole growth, this pattern makes a certain kind of sense. Perhaps this is simply a brief transitional stage that galaxies and their central black holes pass through early in their development, one that becomes rarer over cosmic time as galaxies and their black holes settle into different, less extreme states of activity. But confirming that interpretation and understanding exactly why this transition happens and what triggers it remains an active area of ongoing research. What makes untangling all of this so genuinely difficult is the sheer distance and faintness involved. These objects are so far away that their light has been traveling toward us for well over 13 billion years, and by the time it reaches Webb's mirrors, it has been stretched, dimmed, and altered by the expansion of the universe itself in ways that require extremely careful technical correction before any meaningful interpretation can even begin. Every little red dot in these images represents an enormous investment of observing time and computational analysis just to extract a usable spectrum, let alone to definitively determine what physical process is producing the light in the first place. Astronomers are, in a very real sense, trying to diagnose the internal workings of an object based on an extremely faint, distorted signal that has crossed nearly the entire observable universe to reach us, degraded and reshaped at every step of that impossibly long journey. And yet, despite all of that difficulty, the sheer number of little red dots being found is itself scientifically significant, independent of exactly what each individual one turns out to be. If even a substantial fraction of them do turn out to be actively growing black holes, their sheer abundance would mean that vigorous early black hole growth was a far more common, far more widespread phenomenon in the young universe than any pre-Webb model had anticipated. This has real implications for one of the most persistent open questions in cosmology. How exactly do galaxies and the supermassive black holes at their centers grow together over cosmic time, influencing and constraining each other's development in ways astronomers are still working to fully map out? Every little red dot that gets successfully studied in detail adds one more data point to that much larger puzzle, one small red smudge at a time. There's also a genuinely humbling scientific lesson embedded in this entire story, one that goes beyond the specific mystery of what little red dots actually are. Webb was built with an enormously ambitious set of scientific goals, carefully planned out over decades of design, engineering, and painstaking construction. And yet, almost immediately upon beginning its science operations, it stumbled into something nobody had specifically predicted or planned for, an entirely new, numerous, genuinely puzzling population of objects that simply hadn't shown up clearly in any previous telescope's data, hiding in plain sight in the very deep field images the mission was always going to capture. This is, in many ways, exactly how the best kind of scientific discovery tends to work. The most careful planning imaginable still cannot fully anticipate what a genuinely more powerful instrument, looking somewhere no one has ever looked with this level of detail before, will actually reveal once it opens its eyes. So where does this leave us right now, years into the debate? The honest, current scientific consensus is genuinely unsettled, and researchers openly acknowledge that. Many astronomers now believe that little red dots most likely represent a mixed population, some genuinely dominated by hidden, actively growing black holes surrounded by thick dust, others perhaps better explained by dense, compact bursts of early star formation, and possibly some combination of both effects happening within the very same objects simultaneously. Ongoing observations, using Webb's full suite of instruments to gather more detailed spectra, alongside careful statistical analysis comparing larger and larger samples of these objects, are gradually narrowing down which explanation applies, in which specific cases, slowly turning a genuine mystery into a more precisely mapped scientific picture. But for now, these small red smudges, easy to overlook amid the vastly more visually striking sweeping galaxy images that usually make headlines, remain one of the more quietly fascinating open puzzles in modern astronomy. They sat there, hidden in plain sight, in some of the very first images Webb ever released to the public, waiting for someone to notice that something about them didn't quite add up. And in a very real sense, they still are waiting, patiently, for astronomers to finish the painstaking work of figuring out exactly what kind of object can shine so distinctly red, cluster so densely in the universe's earliest chapter, and then largely vanish as cosmic time moves forward, leaving behind only their strange, persistent glow, sitting quietly at the very edge of what our most powerful telescope can see.